VHDL delay types. There are three types of delays in VHDL: delta delay, inertial delay, and transport delay. Let us look into each of these. Delta delay is an infinitesimally small delay that allows for ordering of the events that occur in the same simulation time. It is to be noted that whenever we assign a signal with a value, it doesn't change as soon as the signal assignment statement is executed. Rather, the assignment schedules a transaction for the signal which is applied after the process suspends. Thus, the process doesn't see the effect of assignment until the next time it resumes, even if this is at the same simulation time. This delay of 0 femtoseconds in a signal assignment is called a delta delay. In a delta cycle, the simulation time doesn't advance. Each simulation time can be considered to contain an infinite number of delta delays, and hence there can be multiple delta cycles within a simulation time. Time advances when there is no activity in a given simulation time to the point where the next activity is scheduled, and that could be due to delayed signal assignment, which we see in the coming slides, or due to a suspending a process until a future time using wait for statements. Inertial delay is the default delay used in VHDL. In real devices, changing the values of internal nodes and outputs involves moving electronic charge around in the presence of capacitance, inductance, and resistance. This gives the device some inertia, and it intends to stay in the same state unless we force it by applying inputs for a sufficiently long duration. Hence, the inertial delay is suitable for modeling delays through devices with inertia. Example, logic gates. The input should be stable for a specified amount of time given by the pulse rejection limit to propagate to the output. If a gate has an inertial delay t, it delays the input by time t, and any pulse with a width less than t is rejected. This delay is used to filter out unwanted spikes and transients on signals. Note that the keyword inertial is not compulsory. The general syntax is as shown. Here, the pulse rejection limits dictates the amount of time for which the input has to be stable in order to reflect at the output. Inertial is the keyword. The value given out by the expression is delayed by a time specified by the inertial delay value. And if any input changes is less than the pulse rejection limit, that particular pulse is suppressed. If the reject pulse rejection limit option is not specified, then the inertial delay value is considered to be the pulse rejection limit. For example, if inert underscore delay is assigned with signal A after 2 nanoseconds, implies all the spikes of less than 2 nanoseconds is suppressed and the value of A is delayed for 2 nanoseconds and assigned to inert underscore delay signal. Similarly, reject underscore delay signal is assigned with the value of A delayed for 10 nanoseconds. If there are any pulses of less than 4 nanoseconds, those pulses are suppressed. Transport delays is used to model an ideal device which has an infinite frequency response, that is, the hardware has no inertial delays, and no matter how short the input pulse is, it reflects at the output. Example, an ideal transmission line which transmit all input changes delayed by some amount. This delay just represents pure propagation delay. All the spikes and glitches are propagated. To use the transport delay model, the keyword transport must be used in the signal assignment statement. Example, trans underscore delay is assigned with the value x delayed by 10 nanoseconds. Let us create a small example using these constructs and observe the behavior. Declare an entity delay with an empty port list. Declare an architecture RTL of delay. Declare signals A trans underscore delay, reject underscore inert underscore delay, and default underscore inert underscore delay. In the process delay P, we declare the signal assignments with transport and inertial delays. Trans underscore delay should be an exact copy of A but delayed by 10 nanoseconds. Reject underscore inert underscore delay should be a delayed version of A minus the pulses which are less than 4 nanoseconds. Default underscore inert underscore delay is same as A delayed by 10 nanoseconds minus the pulses less than 10 nanoseconds. In the process stimulus, we apply the stimulus on input signal A such that we can observe all possible scenarios. Let us run the simulation. Here we use Xcelium simulator and observe the waveform and see how the delay statements behave. Select the top file, add to waveform window, run the simulation, adjust the time scale and the zoom option. We see that the signal trans underscore delay is the exact copy of A delayed by 10 nanoseconds. The short pulses of duration 2 nanoseconds and 4 nanoseconds is also transmitted, and hence we can say that it doesn't remove any spikes or glitches. The signal reject underscore inert underscore delay should be a delayed version of A delayed by 10 nanoseconds minus all the pulses or changes which are less than 4 nanoseconds. Here we can see the change at 14 nanoseconds containing a 2-minute pulse and also at 21 nanoseconds containing a 4 nanosecond pulse are eliminated. We see that at 12 nanoseconds there is a 2 nanosecond pulse which is suppressed. At 21 nanoseconds there is a 5 nanosecond pulse which is greater than the 4 nanosecond rejection limit specified, and hence this particular pulse is passed to the output. Next we have the default inner delay signal for which the pulse rejection limit is 10 nanoseconds, and hence the pulse at 14 nanoseconds and 21 nanoseconds are eliminated as they are less than 10 nanoseconds. This is in accordance with the definition of the delay